Hi class, this is the first video lecture for chapter 12, chapter 21. So it's nuclear chemistry, and this is going to be covering section 21.1. And you can get started on this as soon as you've completed chapter 12.1 kinetics. So let's go. I'm going to share my screen as usual and take a look at this PowerPoint. We do have a worksheet at the end to do also. You can see that up on the screen. So let's go to the PowerPoint. Let me see, here we go. Chapter 21, so point 1. So in this section, I'm going to try to look at what makes nuclei stable and unstable, and also calculate this term called the mass defect and calculate binding energy. And so when we're talking about nuclear chemistry, we're not talking about the kinds of chemistry that we studied you have been studying, that involves molecules and atoms reacting together to form new substances. In nuclear chemistry, we're talking about changes that occur in the nucleus of atoms. And so we're not combining atoms to form new compounds, but indeed sometimes when a nucleus decays, it's called nuclear decay or radioactive decay, it does change into a new substance. So this is the only time when a few of the laws that we talked about in chemistry aren't obeyed. So one substance can turn into another. So one atom can turn into another atom when we're talking about nuclear chemistry. One type of atom will turn into a different type of atom, or one element will change into another element. And when something like that occurs, we always said there was conservation of mass. When we look at chemical reactions, well, in nuclear reactions, there's not conservation of mass. So what there is there's conservation of mass and energy. So when we lose mass, we produce energy in a nuclear reaction. And so that's a big difference from what we've been studying previously. So let's look at the next slide. So when energy is given off spontaneously from the nucleus of an atom, it is called nuclear radiation. And we've talked about radiation before. Another term for radiation is electromagnetic radiation, and that's really the study of light. And it involves wavelengths and frequencies. And it can go from radio waves all the way to X-rays, and all of those are can be produced by compounds and atoms. The particular radiation that we're talking about now comes from the nucleus of the atom. The other types of radiation have to do with the electron shells that are outside the nucleus. So X-rays come from X-rays and UV radiation and infrared all have to do with what's going on with the electron shells or with the chemical bonds, electrons in the chemical bonds. But this radiation we're talking about now specifically comes from the nucleus, so it's called nuclear radiation. And when we have an atom that is producing nuclear radiation, we call that atom radioactive. And not all atoms are radioactive. But the radioactivity occurs because the nucleus is unstable. So it's you might think of it as having too much energy. Too much energy is stored in the nucleus. And so it releases some of this energy to become more stable. So radioactive atoms that are producing this nuclear radiation are doing that to become more stable. And I think everybody's heard of uranium, and uranium's a natural occurring radioactive element. Well, uranium eventually turns into lead, which is a stable isotope. So we learned about isotopes previously in Chem 2A. And the isotopes that we're going to be talking about in this chapter are radioactive isotopes. And it turns out there are a lot more radioactive isotopes than there are stable isotopes among all the possible atoms. Another name for a radioactive substance, or it's called a nuclide. So sometimes you'll hear radionuclide is another name for a radioactive substance. So instead of saying a radioactive element, you might hear the term radioactive nuclide, Nuclide. So every element has at least one radioactive isotope or radioisotope. All the elements above atomic number 83 are radioactive. In this particular bullet point, there's a link to a interactive table, periodic table. So if you look at, say, cobalt, let's look at cobalt here, right in the middle of the periodic table. So cobalt has several isotopes. Let me see. Let's go back quickly. We'll go to isotopes. I'll go to cobalt, and it shows all the isotopes of cobalt. So if we go up here, let's look at cobalt 60. It turns out cobalt 60 is a radioactive isotope of cobalt. And there's some information about it over here. It has a half-life of 5.27 years. I think it said it decays with, let's see, cobalt. What's the primary decay mode is beta, gamma. So it says here the decay mode is beta and gamma. It tells you how much energy that beta particle has when it leaves the cobalt 60 nucleus. So if you're interested in that interactive table, you can come back to this PowerPoint, click on this link, and you'll come right to this interactive periodic table. It's pretty cool. Up here at the top is the link, so you could also find that. You know what they might do? I'll put this link to the interactive periodic table in our Canvas module for this chapter. So I said there are many radioisotopes known. So there's more than 3,300. Many have been made by humans. And we're going to talk about that later in this chapter, how those are made. In contrast, there are only about 265 stable isotopes among all the elements. So we're going to talk about what makes an isotope or an atom stable and what makes it not stable. So here we have a graph showing the number of neutrons on the y-axis and the number of protons on the x-axis. Oops, sorry. Here we go. Okay, so the y-axis, the x-axis, and it's the ratio. This plot, this solid line here shows this is the line where the ratio of neutrons to protons is 1 to 1. So you can follow that. 30, if there's 30 protons, there's 30 neutrons. This heavy blue line in this green zone shows the position of the stable isotopes along here. So these are the stable isotopes on this blue line. You can see that initially the ratio of protons to neutrons for stable isotopes is about 1-to-1. But as we increase the number of protons, go up in the periodic table, this diverges where the stable nucleus has to have more neutrons than protons. The green zone are where all the radioactive elements exist. So if the ratio of protons, excuse me, if the ratio of neutrons to protons is too small, you're in this zone below the solid blue line, and those atoms are radioactive. If the ratio of neutrons to protons is too large, you're above this solid line, and the atom is radioactive. I have a couple notes here. It says if the ratio is too large, which means you're in this zone, the atoms typically decay by beta decay. And what beta decay is, what we're going to learn is that when a nucleus undergoes a beta decay, the number of protons increases. So when we do beta decay, the P goes up, the N goes down, so this ratio gets smaller, and so the element becomes more, or that atom becomes more stable. The nucleus becomes more stable. It's closer to the solid blue line. If the N to P is too small, we do a thing called electron capture. So that's where the nucleus actually steals an electron from one of the outer shells, one of the electron shells. And when that happens, the number of neutrons goes up and the number of protons goes down in the nucleus. And so, again, the nucleus, the ratio for the neutrons to protons in that nucleus gets closer to this blue line. Now, this blue line is interesting. The blue line stops up here at a atomic number 83. That's the last stable element. All the elements above atomic number 83, remember the elements go up to 118, are all radioactive. All the isotopes, all the atoms of the elements, every isotope of all the elements above 83 are radioactive. So there's a little note here on the side that says, as nuclei get larger, it takes a greater number of neutrons to stabilize the nucleus. And if you think about it, the nucleus is extremely, extremely small, and it's packed with protons, and there's a huge repulsion that goes on between these protons. Well, the neutrons help to provide a buffer or a shield for that repulsion. And but as the number of protons increases, it takes more and more neutrons to help stabilize that the nucleus. But that's not the only thing that's going on. It turns out there's a strong force called the nuclear strong force. There's a couple of forces and energies going on in the nucleus that help hold it together. And one of those is called the nuclear strong force. And there's a way to estimate that. So that's what we're going to do. So this sheet shows something about the nuclear strong force. So the nuclear strong force is called the binding energy. So we're going to be able to calculate the binding energy for a nucleus. And it turns out that if you take the, remember nucleus, the nucleus is made up of protons and neutrons. And these are called nucleons. And so we can calculate this binding energy, or the strong nuclear force, strong nuclear energy. Strong nuclear force is called binding energy. We can calculate that for an isotope. And if you divide by the number of nucleons that are in the nucleus, the total number of neutrons plus protons, you get this binding energy per nucleon. So this scales in million electron volts, MeV. It could be in joules, could be in calories, any energy unit. But million electron volts, MeV, is pretty common when you're talking about nuclear chemistry, units of energy in nuclear chemistry and nuclear radiation. So along the x-axis is the mass number. You know, that's the same, that's the total number of nucleons, the mass number. So it's protons plus neutrons. And so these are the simplest elements. So protons plus neutrons, that's about maybe 9. So it'd be, I don't know, an element like beryllium or something. But if you take the binding energy, calculate the binding energy for a radioactive atom divided by the number of nucleons, total number of nucleons, you'll get the binding energy per nucleon. And so as you increase mass number, this increases until it kind of peaks out at around mass number 56. Mass number 56 is has the highest ratio, or the highest binding energy per nucleon. So that's considered the most stable nucleus. The highest binding energy per nucleus, the most stable nucleus. And that element happens to be iron. So a lot of people consider iron to be the most stable element. I'm not sure if that has anything to do with the fact that the Earth's core is made out of iron. I don't know, maybe it does. But the nucleus of iron atoms is the most stable nucleus. That's really the end of this discussion, this PowerPoint on 12.1. What I want to do now is actually, if you've read chapter 12.1, you notice there's quite a few calculations on calculating this binding energy. So that's worksheet 6. And let's go to that now. So get out of the PowerPoint. And I'm going to go over this worksheet. Let's see. So come on. Okay, speaker, the one, that one, there we go. This one. There we go, finally got it. Okay, so here's the worksheet 6. So I've actually worked this out ahead of time. These calculations, the numbers are kind of big. So it just takes a long time to write them down and to enter them in, write down, enter in the calculator. There's a lot of scientific notation in doing these calculations. So anyway, so I did all these calculations ahead of time. I'm just going to go walk through them, so it won't take so long. But I want to point out this table here. So these are some really important values and some constants. I've labeled this table useful data. So this is something that you want to have handy when you do the homework and also when you take the exam. So there's lots of really good information here. It tells you what the masses are of the subatomic particles that we're concerned with. So electron, it has the relative masses in atomic mass units. And so this is the symbol for atomic mass unit, if you don't remember. So it's just a U. So it stands for AMU. So that's the mass of an electron in AMUs. It's 5.485779 times 10 to the minus 4. And this is the mass of a proton and the mass of a neutron, and the mass of the neutron is slightly greater than the mass of the proton. These are the masses of the same subatomic particles in kilograms. You can do these calculations for binding energy using either of these masses. Down here are some units where we've converted mass into energy. And so mass into energy is converted using Einstein's equation, E equals mc squared. So we're going to do that in the first problem. But the way this table, the way these values were determined, these all came from E equals mc squared. And there's just various units of energy relating to various masses. So here we have the conversion from million electron volts to joules. Here we have joules to kilograms. Here we have AMUs to kilograms to joules. Well, this is really a table of conversion factors if you want. Here's another one that says 1 AMU is 931.5 million electron volts. So you don't have to use all these all the time. It depends on what information you're given. So let's look at the first problem. So it says using E equals mc squared, calculate the energy in joules for 1 AMU. So here's our equation. Here's some useful information for that. C is the speed of light, 3 times 10 to the 8th. That should be 10 to the 8th. 10. 3 times 10 to the 8th meters per second. 1 joule is 1 kilogram per meter squared per second. So when we use E equals mc squared, where m is in kilograms, we end up with kilograms meters squared per second, which is 1 joule. Okay, so that's an easy conversion from the kilogram meter squared per second into joules. It's 1 to 1. So let's look at this calculation. So E equals mc squared. The mass of 1 AMU in kilograms is found up here in this table. So we'll go right up here in the table. There's the mass of 1 AMU in kilograms times the speed of light, 3 times 10 to the 8th meters per second squared. So you should always have that handy. That wasn't on this original worksheet. I added that. So we do that calculation, you get 1.494 times 10 to the minus 10th kilograms, kilogram meter squared per second squared, and that converts directly into joules, 1.494 times 10 to the minus 10th joules. So those are the steps you'd go through to calculate joules from E equals mc squared. So you need to have the mass in kilograms of 1 AMU. So that's, we can write a conversion factor down here now. 1 AMU equals 1.494 times 10 to the minus 10th joules. So that's what we just calculated. And that's what's up here in this table. 1.494 equals 10 times 10 to the minus 10th joules. If you have any questions on this worksheet or how to do these problems, or the thinking that goes into it, if I skipped over something or gone too fast, just join me in office hours and we can go over these again in some different detail. So here's another problem. It says if helium-4, so here's the symbol for helium-4, 2He superscript 4. Helium-4 is the most abundant isotope of helium. Its mass is 6.6447 times 10 to the minus 27 kilograms. So that's the mass of 1 helium atom. It says, how many nucleons are there in helium-4? Well, that's easy. There are 4. That's what the 4 means. There's 4 neutrons plus 4 protons. So we have 2 protons plus 2, excuse me. There's 4 nucleons that are made up of 2 protons and 2 neutrons. So we have a 4 total. What is the calculated mass of helium-4? So we can calculate the mass of helium-4 by adding up all of the masses of all the subatomic particles. So in helium-4, we have 2 protons, 2 neutrons, and 2 electrons. So we just multiply 2 times the mass of the protons, which is 1.673 times 10 to the minus 27, obtained from the data table above. That comes out to be 3.346 times 10 to the minus 27. We have 2 neutrons, so that's 2 times 1.675 times 10 to the minus 27 equals 3.350 times 10 to the minus 27. That's the mass of 2 neutrons in the helium nucleus. And then we're doing the mass of the whole atom, not just the nucleus. So we have to add the mass of the 2 electrons. So 2 electrons times 9.109390. I cut off in 3 decimal places, times 10 to the minus 31 kilograms. 2 times that equals, that's not right. I've got to fix this. 9.109 times 2, that would come out to be 1.8, shoot. It comes out to be 18, I'll write it 18.218 times 10 to the minus 31. So I wonder if that changed my mass. Let me see, we have to do a calculation here. I thought I had this all figured out. 18.218 exponent minus 31 plus 3.350 exponent minus 27 plus 3.346 exponent minus 27. If I add all those together, I get 6.698, 6.697. Well, it's pretty close. This should be 6.698 instead of 7. Let's see how that changes it. So what is the mass defect? So we're going to take 6.698, which is our calculated mass. Well, let me back up a minute. The mass defect is the calculated mass, the mass we just calculated from here. Here's our mass, calculated mass, minus the actual mass. Now the actual mass is what's given up here. It says the actual mass is 6.6447 times 10 to the minus 27. But if we add up all the masses of all the subatomic particles, we get a mass that's 6.698 times 10 to the minus 27. That's larger. So the difference is called the mass defect. So if we subtract 6.645 times 10 to the minus 27 from 6.698 times 10 to the minus 27, we get a mass defect of 5.22, and I have to add one more, 5.223 times 10 to the minus 29 kilograms. No, that's not. So let me see, 6.698 minus 6.645 53. Jesus. This comes out to be 5. 5.3 times 10 to the minus 29 kilograms. So what is the binding energy of the nucleus in joules? So I have to change this to 5.3. And we multiply it times our conversion factor of joules to kilograms that we can find up above here. So let's go back up to the top to this special table that's so important in these kind of calculations. 1 joule is 1.111 times 10 to the minus 17 kilograms. So I want this in joules. I want kilograms to cancel, so I'm going to put 1 joule over 1.11 times 10 to the minus 17 kilograms. And because my mass defect changed a little bit, I'm going to have a little bit different value for the number of joules. So I had to go through this calculation anyway. And I get 4.77 times 10 to the minus 12. So it's a little bit larger. 4.77 times 10 to the minus 12 joules per nucleus. So that's our answer for that one. So I made a little mistake up above, but it kind of illustrates what kind of mistakes you can make when you're doing these problems, and it's pretty easy to do. The last part of this is what is the binding energy of the nucleus in million electron volts? And so we would take that 4.77 times 10 to the minus 12 joules per nucleus, multiply it times 1 million electron volts over 1.602 times 10 to the minus 13 joules. Again, that's a conversion factor that we find up above in our special table. So if we do that, we end up with a different value. Let's see, 1.77 divided by 1.602 e to the negative 13, and we get 29.8. So it did change a bit. So we ended up with 29.8 million electron volts for the binding energy in this helium nucleus. Now this is a little bit different from the value that this same example was worked in your book, textbook, but this is a little different, and that bothered me. I looked at it, and the reason is because the mass that they give in the book for the helium atom is a little bit different. So that gives a different mass defect, which is going to lead to a different binding energy. So it's close. I think in the book it came out 28.3. It's not that far off, but it's a little bit different because the masses in the book are a little bit different from these masses. Okay, so I have 3 more problems on this side. So you get a lot of practice calculating mass defects and binding energies. So in this case, it says calculate the mass defect and binding energy for the for boron 10 mass of boron-10 is 10.0129 AMUs. So what I did is I labeled this, by the way. Let me put this up here. So I labeled that 10.0129 AMUs as the actual mass of boron, of a boron-10 atom. So what we need to do to calculate this mass defect is to add up all of the the masses of all the subatomic particles, and that's shown in this box. So for boron-10, we have 5 protons, 5 neutrons, and 5 electrons. So we just take 5 times the masses of each of those subatomic particles. And it looks like we calculated those accurately. So if you do that, you end up with calculated mass for boron-10 of 10.08245 AMUs. Well, the actual mass turns out to be 10.0129. We take the difference between those two, 10.08245 minus 10.0129, and we get a mass defect of 0.0696. See. So to figure out what the binding energy is, and it doesn't say what units, so I just chose to do joules. We could have done this in million electron volts, but I took this mass defect of 0.0696 AMUs, multiply it times our conversion factor to go from our energy conversion factor of mass to energy for joules by multiplying it times 1.494 times 10 to the minus 10 joules per AMU. When we did that, I got a binding energy for boron-10 of 1.0398 times 10 to the minus 11 joules. Probably 3 sig figs is enough, so maybe 1.04 would be adequate, times 10 to the minus 11 joules. Now that doesn't sound like very many joules. But remember that this is just for one atom. If you multiply this times a mole of boron-10 atoms, you get a tremendous energy. Remember, a mole is 6.022 times 10 to the 23rd atoms. And so if you multiply this times 6.022 times 10 to the 23rd, you're going to get something like, what, 23, 12, 10 to the 12th joules. So 10 to the 12 joules is a lot of joules. That's a lot of energy stored inside the nucleus of those atoms. Okay, so far we've been looking at just the binding energy that's holding a nucleus together. But when a nuclear reaction occurs, energy is released. And so here's an example of a fusion reaction between hydrogen atoms. And it says, the statement says, this fusion reaction is one of the final stages in the fusion process that occurs in the sun. So we have hydrogen 2 reacting with hydrogen 3, that's deuterium and tritium. These are the names of those isotopes of hydrogen, producing helium 4, which we learned earlier was the most stable and most abundant isotope of helium. That's a stable isotope of helium and is not radioactive. Tritium, this isotope of hydrogen, is radioactive. That gives off beta particles. Deuterium, hydrogen 2, is a stable isotope of deuterium. So anyway, when this fusion reaction occurs, you get a stable helium atom plus a neutron. So the question is, well, how much energy is released? So if you can think of it, this neutron comes out of this fusion reaction with a certain amount of energy. So the way to do that is, again, it's when these reactions occur, remember the difference between a nuclear reaction and a chemical reaction is that nuclear reactions don't have conservation of mass. So to calculate the energy, we're going to see what the mass difference is between the reactants and the products, and the mass difference is going to be equal to the energy released when this nuclear reaction occurs. And so this problem has the masses of all of the reactants and the products listed. So we have deuterium, tritium, which are the reactants. We have hydrogen or helium-4 and a neutron, and the masses of each of those. So I put a little arrow here to show the combined mass of the reactants is at 8.353 times 10 to the minus 27. I did that right, I hope so. And the combined masses of the products is 8.322 times 10 to the negative 27. The difference between those, so it's down here. We've got the mass of the reactants minus the mass of the product is the mass released as energy. That's 3.1 times 10 to the minus 29 kilograms. If we multiply that times our conversion factor of kilograms to joules, which is up here in the statement. So I included that so you don't have to go back and look at our, that came from the table on page 1. We end up with 2.79 times 10 to the minus 12 joules being released as energy in this fusion reaction. So again, if you want to know how much, if we had a mole of this and a mole of each of these, it produced a mole of helium, you can calculate, you just multiply this value times Avogadro's number, multiply 2.79 times 10 to the minus 12 joules by Avogadro's number, and you get the number of joules per mole, which would be an incredibly large number. And that's, excuse me, if you talk about a fusion bomb, that's what happens in a fusion bomb. A hydrogen bomb probably only needs a mole of hydrogen to blow up a whole city. That's how much energy would be released. Hydrogen bomb is a fusion bomb. Okay, the last problem here, we talk about the binding energy per nucleon. So this is a little bit different. So each of these problems on this worksheet are approaching this binding energy from a little bit different angle. And in this case, we're given the binding energy per nucleon for potassium 40. So that's 8.538 million electron volts. So here's another unit of energy. So we're going to do this problem with a different unit of energy. So this is the there's 8.538, I'll just stop there, million electron volts per nucleon, but there's 40 nucleons. That's what potassium 40 means. It means it's 40 nucleons, 40 protons and 40, or well, the sum total of the neutrons plus the protons is 40. So to find out what the total binding energy is in the nucleus, you have to multiply 8.538 times 40. So that's what I've done here, times 40. And I get the total binding energy for a potassium 40 atom. 341.52 million electron volts per each potassium 40 atom. So the first question is, what is the mass defect for potassium 40 in atomic mass units. So I've got a little conversion factor here. 1 AMU is equal to 931.5 million electron volts. Again, that came from that table on the front page. So the binding energy, here's what we learned about. The binding energy comes from the mass defect times the binding energy in million electron volts comes from the mass defect times 931.5 million electron volts per AMU. Remember the mass defect unit, the unit for mass defect would be AMU. So I'll put a U there. So the U's cancel and we get our binding energy in million electron volts. Well, our calculation of the binding energy in the nucleus was 341.52 million electron volts per potassium-40 nucleus. And so we have a simple equation here where we have the mass defect. So what's the mass defect? That's what we're looking for. The mass defect times the conversion factor equals the binding energy. So if we simply divide the binding energy by the binding energy per AMU, we'll get the mass defect in AMUs. So that's what I did. 341.52 divided by 931.5 is going to give us our mass defect in AMUs, and that turns out to be 0.3666 AMUs. The last problem says, what is the energy in units of kilojoules per mole of potassium-40 atoms? And in this case, what we need then to do is to convert the binding energy into joules and then multiply it. So we have to convert the MeVs. So here's the MeV up here. This is the binding energy that we calculated for a nucleus. But this question is about kilojoules. So we need to convert million electron volts into kilojoules. That gives us kilojoules per atom. But then this question says, how many kilojoules are there in a mole? I've been talking about that, how tremendous, what a big number that is. So let's see what it is. That's what this problem is about. So we have 341.52 million electron volts in a potassium-40 atom. If we multiply it times our conversion factor to get kilojoules per atom, we just multiply that times 1.602 times 10 to the minus 13. This should be 13, not 16, sorry, minus 13. And then we're going to multiply it times a mole of atoms, 6.022 times 10 to the 23rd. When we do that, we end up with 3.29. I think that's a 9. Let me do the calculation. I hate to do this calculation. It's either 9 or 7. I think it's a 9. I think it's 3.295. Not a very good 9. Times 10 to the 13th. You might want to check that when you're working this problem yourself. Kilojoules per mole of potassium-40. So 3.295 times 10 to the 13th kilojoules. Well, that's a huge number of kilojoules. I guess if we divide it by, if you can relate to calories better, you can divide it by the number of joules in a calorie, which I think is 4.312 or something like that. And you get how many calories? Well, there's about 10 to the 13th calories. It would be kilocalories, 10 to the 13th kilocalories. Well, that's hard to fathom how much energy that is. But that's how much energy is in the holding the nucleus of potassium-40 atom together. So that's about it for section 21.1. And so I'm going to sign off for now. And if you have any questions, as always, drop in the office hours or send me an email or a text message. Okay. So I'm going to end this meeting. You guys take care.